My dear students, I welcome you to third lecture of Module 5. In today's lecture, we are going to discuss modern HVDC power transmission system, which is also called HVDC Light or HVDC Plus. So I will write here HVDC Light or HVDC Plus. The question is, why is modern HVDC system called HVDC Light or HVDC Plus? Actually, HVDC Light or HVDC Plus is a trade name which is given by two leading pioneering companies. One is ABB. ABB calls it HVDC Light, and another company is Siemens. Siemens calls it HVDC Plus. Okay, the trade name given to modern HVDC systems is HVDC Light as given by ABB, or HVDC Plus as the name given by Siemens. Okay, now the question is, why are we now shifting from classical HVDC systems to modern HVDC systems, or why are we shifting from classical HVDC systems to HVDC Light or HVDC Plus? It's because of the fact that in classical HVDC systems, we encounter some problems. Let us first of all identify what are the main problems in classical HVDC systems. I will write here main problems with classical HVDC technology. Main problems with classical HVDC technology. Let us try to identify what are the main issues or what are the main problems with classical HVDC technology. The first issue with classical HVDC technology is that it is mostly used for long distance point-to-point transmission. So it is mostly used for long distance point-to-point transmission. Point-to-point transmission. What does it mean? It means, I have already discussed this point with you while discussing the main features of HVDC systems. Classical HVDC system is suitable only for bulk power transmission. I mean, when you have to transmit huge blocks of power, and of course over very long distances. Because if you try to design and install an HVDC system for short distances, then it will be very costly as compared to AC power transmission system. As you already know, up to the breakover distance, AC transmission system is cheaper than HVDC transmission system, and only beyond breakover distances, HVDC transmission system becomes economical. So therefore, since right now in the world over, the breakover distance is around 500 kilometers. So we can say the general rule is that up to 500 kilometers AC power transmission is cheaper, and beyond 500 kilometer transmission length, HVDC transmission is cheaper. So that's what I have written here. This is the issue with HVDC, classical HVDC power transmission technology. That is, it's mostly used for long distance point-to-point transmission. So only when long distance power transmission is required, and it is required to transmit bulk amount of power, huge blocks of power, then only this technology is feasible, and it is cheap, it is economical, and it is efficient. Now, the problem with point-to-point transmission is that, for example, if you have an HVDC transmission system which is covering a distance of 1000 kilometers, okay, if you need power in between, so say for example you are starting transmission from area A and you are transmitting power from area A to area B through HVDC transmission lines or HVDC transmission system, and the total distance or length of transmission line is 1000 kilometer. Say on the way of transmission line, say somewhere at after covering 500 or 600 kilometers, a large industrial load is located there, and you want power for this industrial load. Is it possible to tap power from HVDC long distance HVDC transmission line and supply this power to industrial load? My simple answer is no. It's not possible because our classical HVDC power transmission system is point-to-point transmission. Point to point means you are transmitting power from point A to point B. In between, if there is point A dash or point B dash, you cannot supply power to those intermediate points A dash and B dash. That is the problem with classical HVDC power transmission system. Now you may now with some modifications in classical HVDC transmission systems, like nowadays instead of going for two-terminal HVDC system, we go for multi-terminal HVDC systems. Multi-terminal HVDC systems means we don't have two converting stations. See, in classical two-terminal HVDC systems, we have two converting stations. One converting station is operating in rectifying mode, and another converting station at the other end is operating in the inversion mode. So that is point-to-point transmission. But nowadays the trend is that instead of going for two-terminal HVDC transmission, one should go for three-terminal or four-terminal, or in general one should go for multi-terminal HVDC transmission system. So in multi-terminal HVDC transmission system, say for example you have a three-terminal HVDC transmission system, so you have three converting stations. One converting station, say at end A, another converting station very far off, say after a distance of 1000 kilometers at point B. Then in between you can create another converting station, say at a distance of about 500 kilometers. Okay, so you will have three terminals or three converting stations. Converting station at A, converting station at B, and in between another converting station. So that is called multi-terminal HVDC transmission system. So बीच वाला जो converting station जो आपने create किया, the converting station which you have created in between the two converting stations, you can use this converting station for feeding power to a large industrial load which is on the way of this transmission line. But if you do it like this, the cost will increase, because you have to see, already you had two converting stations. Now you have to create another converting station in the middle. So that converting station, excuse me, that converting station will result in huge costs. So although you can use multi-terminal HVDC systems for feeding loads in between, okay, for tapping power over the transmission line in the middle of, say, in the middle or in the center of the DC transmission line, but this technology is very costly. You have to weigh the cost of technology and you have to see whether it is feasible, whether it is economical to supply this industrial load using multi-terminal HVDC system or not. Another point which I told you, that classical HVDC power transmission system is mostly used for long distance. Okay, can it be used for short distance? I told no, because for distances less than breakover distance, this technology becomes costlier. However, I have already discussed with you back-to-back ties, back-to-back HVDC transmission, which are short distance transmission ties, transmission lines. Okay. But here the purpose is not to transmit bulk power from one point to another point. The main purpose, if you remember, the main purpose of back-to-back HV transmission system is control of flow of power. I mean, if you if you have region A and you want to transmit power from region A to region B through HVDC transmission system, you will have a back-to-back HVDC transmission system. The distance between region A and region B is small, but the purpose is not to transmit bulk power from A to B. The purpose is to transmit controlled amount of power from A to B. And if the need arises, the power can flow from B to A. I mean, if region A is surplus in generation and region B is deficient in generation, then in that case, you can make power to flow from region A to region B in a controlled way. And it may so happen that in another season, region B may be surplus in generation and region A may be deficient in generation. So in that case, using this back-to-back HVDC transmission tie, you can make reverse flow of power in a controlled manner from region B to region A. That is the main purpose of back-to-back HVDC transmission ties. Okay. So therefore, in the nutshell, I can say that the main problem with classical HVDC technology is that it is mostly used for transmission of bulk amount of power, huge blocks of power over long distances, and it is a point-to-point transmission. It is not possible to tap the power in between. However, you can tap the power in between by using multi-terminal HVDC technology, but that will result in additional cost. Okay, so this is first problem with HVDC, classical HVDC transmission system. Second problem is that it requires fast communication channels between the two converting stations. I will write here, it requires fast communication channels between two converting stations. If you remember, we have already discussed control characteristics and control techniques of an HVDC link. For a perfect control of HVDC link, there should be a strong communication channel between two converting stations. If one converting station is operating as a rectifier and another as an inverter, then in order to make that power to flow from a rectifying station to inverting station in a controlled manner with constant current control, you need a communication channel. I mean, if there is a fault on the inverter side, it may result in increase in the DC link current. And DC link current, you have to maintain, your controller will always try to make constant. So in order to make that DC link current constant, the controller acts very fast, but it needs a communication between the two converting stations. So any fault or any disturbance on one converting station will cause corresponding changes in the controller action on the other converting station. So for this to happen, you need fast communication channels between the two converting stations. So this is another issue. Third is, it requires large reactive power support at both stations. I will write here, it requires large reactive power support at both converting stations. You already know that as alpha increases, as alpha of a converter increases, the power factor decreases. And decrease in power factor means that the converter draws large reactive power. QC means converter reactive power. It draws large reactive power. And the thumb rule is that for a 100 megawatt HVDC line, if over an HVDC transmission line, you want to transmit 100 megawatts of active power, 100 megawatts of power, 60% of reactive power support is required at both terminal stations. So this is a huge requirement. And for that purpose, you need costly reactive power compensation equipments. Okay, so this is another problem. Next problem is that they introduce both characteristic and uncharacteristic harmonics. I mean, the converters, they introduce both characteristic and uncharacteristic harmonics. And to suppress these harmonics, you need thus requiring costly and bulky harmonic filters. To suppress the harmonics, you need costly and bulky harmonic filters. We have already discussed the harmonic analysis and design of harmonic filters over last few lectures, a couple of lectures. And these harmonic filters are very costly and bulky. They occupy a lot of space in the switch yard. Okay, and they make the entire HVDC, conventional or traditional HVDC system, a very bulky system, and cost of these harmonic filters is also very high. Okay, so this is another problem. Another problem is that line commutated or phase commutated converters using thyristor valves are used or employed. See, in classical HVDC systems, we use line commutated AC to DC converters, phase controlled converters, which are based on or which are constructed using thyristor valves. And these thyristor valves are naturally commutated. I mean, whenever they are reverse biased, they are commutated. It is not possible to commutate them when they are forward biased. For commutating them, it's necessary that they are reverse biased. So therefore, PWM technique cannot be used here. PWM technique, pulse width modulation technique, is generally not used. And since PWM technique is not used, so size of magnetics is very large. Size of magnetics means inductances and capacitances, is very large. Okay, so therefore your HVDC, classical HVDC transmission system is very costly, very bulky. You know, the size of inductance and the size of capacitance can be reduced if we operate our converters at a very high frequency, switching frequency, say 5 kilohertz, 10 kilohertz, 20 kilohertz, or so on. But since classical HVDC transmission systems use thyristor valves and phase controlled or line commutated, phase commutated or line commutated converters, we are not able to use pulse width modulation. We don't use pulse PWM technique there. So therefore, these converters operate at 50 hertz frequency, and at 50 hertz frequency, the size of inductance, the size of capacitance, which are part of your filters, the size is very, very large. Okay, and therefore it makes the entire system very, very bulky. So these are some of the main problems with classical HVDC transmission system. First is it requires it's mostly used for long distance point to point transmission. So in between, tapping of power is very, very difficult, and it is not economical for short distance power transmission. It is economical only for long distance transmission. Second is it requires fast communication channels between the two converting stations for better control. Third is it requires large reactive power support at both converting stations for the transmission of power over the line, over the link. Next is the converters introduce both characteristic and uncharacteristic harmonics, and to suppress those harmonics, costly and bulky harmonic filters are required. And finally, the last drawback or last issue, main issue with classical HVDC transmission systems is that line commutated converters or phase controlled converters using thyristor valves are employed, and it is not possible to use high frequency pulse width modulation technique. Therefore, the size of magnetics, inductances and capacitances remains very high, and your HVDC, classical HVDC power transmission system is very costly and very bulky. Now, therefore, because of these drawbacks, the modern trend is that for small power transmissions over small distances, instead of going for costly HVDC, classical HVDC technology, we go for modern HVDC technology, which is called HVDC Light or HVDC Plus. It is called HVDC Light by ABB and HVDC Plus by Siemens. Actually, this HVDC Light, it replaces current source converters, CSCs, by voltage source converters. And that means thyristor valves, that is SCR valves, are replaced by modern self-commutating power semiconducting devices. Self-commutating power semiconducting devices. Semiconducting devices like IGBTs, insulated gate bipolar transistors, IGCTs, GTOs, etc. Generally, we use either GTOs or IGBTs or IGCTs, but most of the low power rating HVDC, these modern HVDC systems, HVDC Light or HVDC Plus, they use IGBTs, insulated gate bipolar transistors. So these IGBTs They have a fast switching operation, very fast switching operation as compared to thyristor valves switching operation, and they can be operated at a very high switching frequency as high as 20 kilohertz. The IGBTs are available, commercially available in the market, which can be operated at a switching frequency as high as 20 kilohertz, whereas thyristor valves can be used only at 50 hertz. So therefore, it is possible to use PWM technique in these HVDC light or these voltage source converters, which are replacing the current source converters. And at higher switching frequency, we reap the fruits of this high switching frequency. Many advantages of high switching frequency are there. Now, the first HVDC, now because in HVDC Light or HVDC Plus, we use voltage source converters. Another name given to this technology is also called VSC HVDC technology. HVDC technology, voltage source converter HVDC technology. It is called HVDC Light or HVDC Plus. It is also called VSC HVDC technology. Why? Because here current source converters are not used. We use voltage source converters because current source converters are replaced by voltage source converters. So this technology is also called voltage source converter HVDC technology. That is VSC HVDC technology. And let me tell you that first HVDC Light pilot transmission of 3 megawatts operating at plus minus 10 kV was established in March 1997 in Sweden. This was the first pilot transmission, HVDC Light powered pilot transmission project, which was installed in Sweden in March 1997. This HVDC Light project, it was used for transmission of only 3 megawatts of power, and the link voltage, it was a bipolar transmission link, and the link voltage was plus minus 10 kV. And first commercial project was of 50 megawatts, 50 megawatts plus minus 80 kV. It was commercialized. It was commissioned in 1999, or 2 years after this. And the length of the line was very short, 72 kilometers. So you can now see HVDC Light can be used over very short distances. 72 kilometers is very short. Can you imagine using classical HVDC technology for a small distance of 72 kilometers? No, because that technology is very costly for short distances. That classical HVDC technology becomes economical only beyond breakover distances, that is beyond 500 kilometers. So for transmitting power over very short distance of 72 kilometers or 30 kilometers or 100 kilometers or just 150 or 200 kilometers, we don't use classical HVDC technology. We use VSC HVDC technology or HVDC Light or HVDC Plus, because it provides the economical means of or cheaper means of transmitting the power. Now, various projects which were launched throughout the world, I can give a brief scenario of that. In fact, it is written on a piece of paper in front of me. It's not possible for me to note down all that. However, I can share that page with you after some time. The first project, commercial project, was commercialized in Gotland, Sweden in 1999. It was 50 megawatts plus minus 80 kilovolt bipolar HVDC link. The length of line was 2 by 70 kilometers. 70 kilometers multiplied by 2 means two lines, one positive line, positive pole and negative pole, each of 70 kilometers. That means the length of transmission line was 70 kilometers. And the purpose was to connect wind farm to load center. Power was generated from a wind farm and it was to be connected to load center. So this HVDC Light or VSC HVDC technology was used because distance was very short, just 70 kilometers. Another project was launched in the year 2002. It was launched at Direct Link Australia, and it was 3 by 60 megawatts. That means 180 megawatt project, and the voltage of the line was plus minus 80 kV, and length was 6 by 65 kilometers. Okay, and the purpose was to connect two regional electricity markets. The third project was also established in the same year, 2002, cross sound cable. It was called cross sound. The name of project was cross sound cable It was established in United States of America, USA. The power transmission was 330 megawatts at plus minus 150 kV. The length of transmission line was just 42 kilometers. And purpose was power transmission to large island. Power was generated at some place, and power was to be taken 42 kilometers away to an island. That was the purpose. Next project was called Murray Link. It was established in Australia in the same year, 2002. The power transmission was 200 megawatts at plus minus 150 kV, and length of the transmission line, DC transmission line, was just 180 kilometers. And purpose was to connect two regional electricity markets and control the power flow. Next project was launched in the year 2005. It was called Troll A Norway, and it was 2 by 40 megawatts at plus minus 60 kV. The length of cable or the length of transmission line was 68 kilometers, and purpose was power compressors to supply power to power compressors to increase natural gas production on oil platform. Okay, the Troll oil platform provides 10% of Europe's oil needs. So to provide power to this Troll oil platform, which provides 10% of Europe's oil needs, power was generated 68 kilometers away, and it was taken to this project through HVDC Light. And another project was launched in the year 2006. The name of project was Estink Estonia. It was launched in Finland. The project was 350 megawatts plus minus 150 kV. The length of line was 105 kilometers. The purpose was improved security of electricity supply in the Baltic states and Finland. So this is the overview of some of the main pilot projects which were launched using HVDC Light or HVDC Plus. Let me discuss with you some of the main advantages of HVDC Light. I will write here advantages of HVDC Light or HVDC Plus or VSC HVDC. These are the three names given to this technology: HVDC Light technology or HVDC Plus technology or VSC HVDC technology. What are the main advantages? First advantage is it is economical. It is economical means cheap. It is economical even in low power range. Low power range over short distances. Over short distances. You know, classical HVDC system is used for bulk power transmission, power of the order of hundreds and thousands of megawatts. If you have to transmit small amount of power, the classical HVDC technology is very costly for that. It's not economically justifiable. But HVDC Light or HVDC Plus or VSC HVDC technology can be used economically even for low power range. You have just now seen in different projects just 50 megawatt or 60 megawatt power can be transmitted over short distances. So this technology is economical, unlike classical HVDC technology, which is very costly for low power range and short distances. HVDC Light technology is economical even in low power range over short distances. So this is one of the greatest attractions of HVDC Light or HVDC Plus technology. Second is real and reactive power is controlled independently. Real and reactive power is controlled independently in two HVDC Light converters or HVDC Plus converters. So you have two converters. One may be operating in rectification mode and another in inversion mode. So in these two converters, it is possible to make the control of real and reactive power independently. I mean, you can control real power independent of reactive power. Similarly, you can control reactive power independent of real power at both converting stations, which is not possible in classical HVDC system. In classical HVDC systems, the independent control of real and reactive power in the two converting stations is not possible, whereas it is possible in HVDC Light or HVDC Plus. Third advantage is it controls AC voltage very rapidly. It controls AC voltage rapidly. I mean, classical HVDC system is based on a constant current technique. But this HVDC light technology is based on constant voltage technique. Here, voltage is DC bus voltage is maintained constant, not current. In a classical HVDC system, link current or line current is maintained constant. But in HVDC plus or HVDC light, link voltage or line voltage is maintained constant. And the control of this AC voltage, control of AC voltage and control of DC voltage also, it's very, very fast because the switches are very fast. Okay. Switches are IGBTs, which are 27 times faster than thyristor valves. Next advantage is no contribution to short circuit. No contribution to short circuit current. I will write within brackets due to very fast control action. Due to very fast control action. Your classical HVDC system also does not contribute to short circuit current, but there the control action is not as fast as in HVDC light. Why control action is very fast in HVDC light? Because in HVDC light, the thyristor valves are not used. We are using modern self-commutating power semiconductor devices like maybe GTO or IGBT, and these modern power semiconductor devices operate at very high switching frequency, at very fast speeds. They turn on very fast. Their turn on time is very, very less. Their turn off time is also very, very less as compared to thyristor valves. So control action obviously is very, very fast. Now what is the next advantage? Fifth advantage. I will write here no need to have fast communication channels. Fast communication channels between two converter stations or between two converting or converter stations. Within brackets, I can write both stations can be controlled independently. Can be controlled independently. I told you just few moments back that independent control of both converter stations is possible. It is not possible to control a converting station independently in case of classical HVDC system. Any change in the parameters of one converting station will change the DC line current, and to maintain the DC line current, your controller quickly takes the action at the other converting station so as to maintain the DC line current constant. We have already discussed in module number 3 previously. So in classical HVDC systems, the independent control of converter stations is not possible, whereas that is not the problem in HVDC Light or HVDC Plus. In HVDC Light or HVDC Plus technology, both the converter stations can be operated or controlled independently, because here we are not supposed to maintain DC line current constant. We are supposed to maintain DC link or DC line voltage constant. And therefore it is easier to control both the converter stations independently. So since you have to you can control both the converter stations independently, you don't need to have communication channels or fast communication channels between two converter stations. Whereas in classical HVDC systems, for better control, for coordinated control between the two converting stations, you need fast communication channels. You don't need those fast communication channels in HVDC Light or HVDC Plus. This is another advantage. Next advantage is that it operates, that's your HVDC Light operates in all 4 quadrants. That means it gives 4 quadrant operation. I will write here 4Q operation, 4 quadrant operation. 4 quadrant operation means, this is your DC line current plus IT, this is minus IT, this is plus DC line voltage, plus this is minus. You can operate, this is your quadrant 1 when DC line voltage and current both are positive. Your converter can operate in quadrant 2 where DC line voltage is positive, but line current is negative. It can operate even in third quadrant, where both voltage as well as current are negative, or it can operate in fourth quadrant also, where voltage is negative but current is positive. So your converter, HVDC light or HVDC plus system can operate in all the four quadrants. It can operate in quadrant 1, it can operate in quadrant 2, it can operate in quadrant 3, or it can operate in quadrant 4. This is called 4-quadrant operation, and it makes the control very, very flexible. So this is another advantage. Next is opportunity. We have an opportunity to transmit power, to transmit large amount of power, opportunity to transmit large amount of power over long distances, via underground cables. So you can use underground cables and you can transmit large power over long distances via underground cables. In case of AC cables, the main problem is the large charging current, which does not make it possible for us to transmit bulk amount of power over AC underground cables. But in HVDC Light, your power is in the form of DC. So underground DC cables can transmit large amount of power over long distances. Next is PWM scheme can be used, or PWM scheme is used. Pulse width modulation scheme is used. Your converter switches are operated in using pulse width modulation technique. Pulse width modulation results in high switching operation of the switches, and because of high switching frequency of converters, both the converters are operated at very high switching frequency, maybe 10 or 20 kilohertz. Size of magnetics is drastically reduced. Size of magnetics, that is inductances and capacitances, which are part of filter, is drastically reduced. And I hope you have studied, you must be knowing that when you operate a converter, a PWM, if you have a PWM rectifier, a PWM rectifier results in almost unity power factor. So you will have nearly UPF, unity power factor operation. Using PWM technique, your converter, both the converters can be operated at nearly unity power factor. So when they are operating at nearly unity power factor, so no need for reactive power compensation. No need for Q compensation. Q means reactive power compensation. You don't need reactive power compensators. Whereas in classical HVDC power transmission systems, you are using phase controlled converters. And as alpha increases, your converters draw more and more reactive power. So you need strong reactive power compensation there. But here using PWM technique is responsible for nearly unity power factor operation. And unity power factor operation means that your converters are not drawing any reactive power, or even if they are drawing reactive power, they are drawing negligible amount of reactive power. So therefore you don't need costly reactive power compensation. And another advantage is that the currents drawn by both the converters may be nearly sinusoidal. So harmonic content in currents is drastically reduced. Harmonic content in line currents is drastically reduced. So this is the advantage. I am now discussing with you the advantages of using pulse width modulation technique. If you are using your converter, controlling your converter using PWM scheme, your converter will draw nearly sinusoidal currents, means harmonic content in the currents will be very, very less. So you don't need costly harmonic filters. So no need of costly harmonic filters. You don't need costly harmonic filters. And even if you need some harmonic filters, the size of those filters will be very, very small. Size of filters is very small. Why size of filters is small? Because you are using at high, you are operating your converter at very high switching frequency, say 20 kilohertz, and at 20 kilohertz the size of inductance and capacitance which are part of your filter is very small. So therefore the advantage of using PWM technique in VSC HVDC technology or HVDC Light or HVDC Plus is that your converter becomes it draws power at nearly unity power factor. You don't need costly reactive power compensators. The current drawn by the converters is nearly sinusoidal, so you don't need costly filters. Even if you need harmonic filters, the size of filters will be very small. So it is because of this, since the size of filter is very small, size of converter is very small, you don't need costly reactive power compensators, the overall size of your HVDC system becomes very small. That is why it is called HVDC Light, L-I-G-H-T, Light. Light means halka, वजन में halka, size में छोटा. So that is why it is called HVDC Light. I will write here, that is, or I will write on the next page. So next is your HVDC Light technology is small and compact. I have already explained it. Because of the PWM technique using IGBT converters, voltage source converters, the size of filter is drastically reduced. Okay, the overall size of magnetics is reduced. So therefore your HVDC system, HVDC Light system is small and compact. That is why it is called HVDC Light. That is why it is called HVDC Light. HVDC Light, L-I-G-H-T. Light means lighter in weight, smaller in size. Okay, that's how it has been named like this. Next is, it is useful in windmills. So in windmills, when you are generating the power using wind farms, whether land wind farms or offshore wind farms, HVDC Light is very useful, because the power generated by windmills is not of the order of thousands of megawatts. They generate power few megawatts, say 50 megawatts, 100, 200 or 300 megawatts. And small power, if you want to transmit over small distances, then classical HVDC technology is very costly. So which technology will you use? Obviously you will use HVDC Light or HVDC Plus technology. So therefore HVDC Plus technology is very useful in windmills. So these are some of the prominent advantages of HVDC Light or HVDC Plus technology. And because of these advantages, the modern trend is that for small power transmission over smaller distances, instead of going for AC power transmission or classical HVDC power transmission, we go for modern HVDC power transmission using VSC HVDC technology or HVDC Light technology, or what we call as HVDC Plus technology. Now let us discuss the principle of operation of HVDC Light. Principle of operation or operating principle of HVDC Light. And HVDC Light will look like this. You have a pole, you have converters. Now you don't have converters using thyristor valves, you have converters using IGBTs. For example, your voltage current source converter is replaced by voltage source converter. So this is one, and another is here. This is the block diagram of your voltage source converters. This is the AC side with reactor or inductor. This may be a small sized filter, harmonic filter here on the AC side, if at all you need the filter. So this is filter. Then this is your converter transformer. As usual, you have converter transformer, and this is AC bus. AC bus. Okay. Now what is the output of voltage source converter? So this is voltage source converter, VSC. It converts AC into DC, and this is your DC line or DC link. In a classical HVDC system, you use DC line reactor, but you don't need DC line reactor here. You need DC bus capacitors. So these are DC capacitors, and the neutral of capacitors is grounded, and this is your voltage converter output voltage VD, which is maintained constant, and this is DC line current ID, which is not constant in this case. It may not be constant. Okay, The technology provides HVDC light converter with a switching speed 27 times faster than the traditional HVDC thyristor controlled converter. So switching speed, I will write here this very important point. Switching speed is about 27 times faster than classical HVDC technology or HVDC system because of the use of IGBTs. Insulated gate bipolar transistors, they replace thyristor valves, and IGBTs are very faster in operation than your thyristor valves. Okay, so the key parts of your I have shown converter on this side. Similarly, on the other side, in another converting station, you have voltage source converters there also. I am showing only the rectifier part. On the inverter side, you have two more. You have the voltage source converters on the other side also. I am not showing that, but that is understood. So the main components of your HVDC light are converter transformer, harmonic filters, reactors, voltage source converters, and DC bus capacitors. Okay, so these are the main components. Now let us try to discuss the operating principle. Okay, in order to understand the operating principle, I will draw this again. These are IGBTs with feedback diodes or anti-parallel connected diodes. This is AC side. The voltage across inductor is delta. Let's call that voltage as delta U. The voltage output of converter is, let's call that UC. The current on the AC side, let's call that IR. Okay, so this is a capacitor, filter capacitor on the AC side. Filter current is IF, and voltage across the capacitor is UF. Okay, so this is the current I. Let us call this current as I, and this current is IR. Now this is its DC link, DC side. Okay, and this is VD, DC side voltage. DC side voltage is VD, DC side current is ID, and this converter, it converts DC voltage into AC voltage. Say for example, it operates as an inverter. See, your HVDC light will comprise of one converter on this side and one converter on this side. A converter on this side will convert AC into DC and create DC link, where DC link voltage is VD, DC link current is ID, and this converter will convert DC back into AC and supply power to the load, which is on this side. Okay. Now the apparent the power transmitted, I can write power transmitted by HVDC light. It is given by this equation. It is given by SB, apparent power. It comprises of active power as well as reactive power, because on the DC side you have only active power, but on AC side you have active plus reactive power. So SB is equal to P plus JQ, that is equal to √3 times UF into IR star. See, what is the converter, what is the AC side voltage? It is UF. And what is the current on the AC side? It is IR. So voltage into current multiplied by √3. If you take the line quantities, √3 times UF into IR, this is the power, apparent power. Voltage into current, it will be in kVA or MVA. So SB is equal to √3 UF. Now what is your IR? You can see IR is this voltage minus this voltage divided by this reactance. So it is UC minus UF. I will write here UC minus UF star. It's complex conjugate divided by what is the, let us suppose the impedance of this line is ZR star. Okay, let's call this equation as equation 1. So this is the apparent power, or this is the total power which is transmitted from DC side to AC side using HVDC light. Okay. Now active and reactive powers, I will write here active and reactive powers are given by reactive powers are given by. Now what is active power given by? You can see active power is given by, if you solve this, this is your SB equal to P plus JQ. If you solve it and simplify it, it will come out to be UF UC sine delta. I'm giving you final relationship without going into mathematics, by omega L. Let's call this equation as equation 2. And reactive power, given to the AC side is UF times UF minus UC cos delta by omega L. Let's call this equation as equation 3, where what is delta? Delta is phase angle or phase difference between UF and UC. What is L? L is equivalent reactance. Equivalent reactance. And omega is equal to 2 pi f is the frequency in radians per second. Okay. So by controlling the magnitude of this VC, UC, inverter output voltage, you can control the reactive power. And if you control the angle between, phase angle between UC and UF, which is delta, you can control the active reactive power. By controlling the delta, that is phase angle between UC and UF, you can control the active power. And by controlling the amplitude of UC, you can control the reactive power. Therefore, active power and reactive power control can be exercised independently. How can you control the active power flow to the load? You can control active power flow to the load if you control delta. Delta is the phase angle between UC and UF, and that can be very easily done using a controller. And how can you control the reactive power independently? Reactive power can be controlled if UC is made greater than UF or UF is made greater than UC. Then you can either generate the active power and give that active power to the load center, or you can consume. Your converter can even absorb the active power. It can either generate, that is supply the active power, or absorb the active power by controlling the amplitude of UC. Okay, so by controlling the amplitude of UC, active power, reactive power can be controlled, and by controlling the phase angle delta between UC and UF, active power can be controlled independently. Let's see. So I will write here for delta greater than 0. UF is leading UC and the active power is transferred from AC to DC, and converter acts as a rectifier. Converter acts as a rectifier. That means, if this delta is if delta is greater than, if delta is if delta is greater than 0, that means UF is leading UC. I mean, if UF is leading UC, there is the power flow from AC side to DC side. In that case, this converter will not act as an inverter, it will act as a rectifier. So power will flow from AC side to DC side. But if delta is less than 0, that means if UC is leading UF, then power will flow from DC side to AC side. This will be the direction of power. So direction of power can be either this or this. If UC leads UF, power can flow from DC side to AC side. In that case, this converter will act as an inverter. And if UF is leading UC, then power will flow from AC side to DC side. In that case, this converter will operate as a rectifier. So this is how direction of power flow is determined. And this delta will, if delta is positive, power will flow from AC to DC side and converter will operate as a rectifier. But if delta is negative, power will flow from DC to AC side and converter will operate as a rectifier. And the magnitude of this delta will also determine how much active power is transferred from one side to another side. Okay. Similarly, for UF greater than UC cos delta, the converter generates reactive power and if UF is less than UC cos delta, it absorbs reactive power. It absorbs reactive power. See, it is also very interesting to see from this equation, if UF is greater than UC cos delta, then this whole quantity will be positive. And positive reactive power means that the converter is generating the reactive power. It is generating reactive power and it is giving reactive power to the load center. But on the other hand, if UF is less than UC cos delta, Okay, then in that case this Q will be negative. That means negative Q means that this converter is not generating, it is absorbing the reactive power. So therefore reactive power control can also be done. So therefore by controlling, therefore this theory shows that the active as well as reactive power can be, the direction of active power control, the direction of reactive power control can be independently controlled, and not only direction but also the magnitude of active power transfer and reactive power transfer can also be controlled independently. And this is one of the beautiful features of HVDC light technology, that there is independent control of active power and reactive power. Okay, so this was about operating principle. Now let us discuss some of the applications of HVDC light. So I will write here, I will write applications. Voltage source converter based HVDC, or what we call as HVDC light or HVDC plus, in AC to DC hybrid transmission. This is its first application. You have a hybrid transmission where you are using direct AC transmission lines without any control, or you are using HVDC light also. So let us see what is the application in hybrid AC-DC hybrid transmission. So for that purpose I will draw this diagram here. This is your HVDC light, this is voltage source converter here, okay, and another voltage source converter is on the other side. And then you have a converter transformer here also. This is AC bus. Similarly here you have AC bus, and then you have converter transformer here also. It may be a step-up transformer, and you may have parallel AC lines here, parallel AC lines, and then you may have step-down transformer as shown, and this is the AC bus. Okay, so this is your voltage source converter based HVDC or HVDC light, and these are normal HVDC. These are normal AC transmission lines, parallel lines. Now these normal parallel lines are supported by HVDC light. Let us see how HVDC light helps the overall transmission system. This is called hybrid transmission system. So as far as rectifier, I will write here, using VSC HVDC, its ability of regulating the DC power can help to damp the oscillations when the system has fault. So let us see how VSC HVDC or HVDC light will help here. Say if this HVDC link would not have been there, you would have only AC transmission lines, then there could have been a fault on this side, or a fault on this side, or fault on the line itself. In the event of a fault, a wide oscillations are generally resulted, and the system may become unstable. So how does this HVDC technology help here? Well, this voltage source HVDC light, in presence of HVDC light, the HVDC light always tries to maintain the DC line power constant. And since it has very fast controllers on this side as well as on this side, even if there is a fault on the AC bus side, okay, the system oscillations will be perfectly damped by this HVDC light. Okay, it will help in damping of oscillations very quickly, and the system will remain in the stable operation. So therefore this hybrid AC transmission system, AC-DC transmission system remains balanced, or it remains stable even under fault conditions with the help of this HVDC light. The second point is, if power demand of receiver side or receiver system increases, the system will lose its ability without HVDC light. See, you have to understand, see, if this receiver side power demand, load power demand increases, your AC system may not be able to fulfill all the power demand. But in presence of this VSC HVDC or HVDC light, so receiver power demand can be, there can be power sharing between this AC lines and DC line. Some of the power which was supposed to flow on AC lines because of increase in the load demand, which would have resulted in overburdening or overloading of these AC lines. This power by power flow control action can be transferred, it can be shared by HVDC line. Okay, this HVDC line or HVDC plus line will take some share of power from AC lines, and therefore the ability of supplying more power on the receiver side can be maintained in presence of this HVDC light. If this HVDC light link would not have been there, then an increased demand on this side would not have been possible to be fulfilled by AC lines because of overloading, and circuit breakers would have tripped. But in presence of this HVDC light, some of the power is shared, some of the power which was supposed to be carried by AC lines, but because of their overloading, so some power is shared by or carried by this DC line. Okay, and it is supplied to the load center. So therefore the system operates stably, and the ability of the system to supply more receiver power increases. So this is another advantage in hybrid AC-DC transmission system. So I can also write HVDC light improves the dynamic performance and keeps the system stable. Okay, whenever there are faults, the system tends to become unstable. HVDC light will improve the stability of the system. Dynamic stability, transient stability of the system increases, and system remains more stable in presence of HVDC light. Okay. I will then write here for conventional or classical HVDC system. A fault on an AC side of inverter may cause commutation failure, as we already know. Let me first write may cause commutation failure in inverter, which will cause DC line voltage VDC to become zero. So it will cause VDC to become zero. This delays the recovery of DC and AC side voltages. Then I will write, since HVDC light or HVDC plus does not suffer from commutation failure, does not has commutation failure. There is nothing like commutation failure in HVDC light, modern HVDC systems. It recovers AC voltage quickly by providing reactive power support. On AC side. So it is very important to understand. Say if again, if you have hybrid AC and DC system, let us consider this hybrid AC and DC system. But let us assume that instead of having HVDC light or VSC HVDC, we have classical HVDC using current source converters, thyristor phase controlled converters. Then in case of the classical HVDC, we have already studied in module 2. In case of collapse of inverter side voltage, suppose there is a fault on the AC side bus on this side, that fault will result in collapse of inverter side voltage, and immediately the inverter will suffer from commutation failure. I am talking of classical HVDC, not modern HVDC. So inverter will go into commutation failure, and if there is double commutation failure, then in case of double commutation failure, you have drawn the waveforms and you have seen from the waveforms that for double commutation failure, the DC line voltage or transmission line voltage almost becomes equal to 0. That's what I have written here. It will cause VDC equal to 0. Okay, as soon as AC side voltage collapses, the inverter suffers from commutation failure, and commutation failure will result in VDC equal to 0. So DC bus voltage will become 0. Okay, DC line voltage. Therefore, this delays the recovery of DC side voltage as well as AC side voltage. Okay, when the fault on AC side is recovered, then you have to first wait for the clearance of the fault. Only when fault conditions are over, only when fault is recovered, then only AC side voltage will be recovered. And when there is recovery of AC side voltage, the commutation failure of the inverter will be over, and then the DC side voltage will also recover. So this recovery of AC side voltage followed by DC side voltage will take time. But since in case of modern HVDC technology, I mean VSC HVDC or HVDC Light, we are using voltage source converters, not current source converters, and there is nothing like commutation failure. There is no concept of commutation failure in these voltage source converters, IGBT switches. These voltage source converters, they do not suffer from a phenomenon called commutation failure. It is only phase controlled converters used in classical HVDC systems which suffer from commutation failure. Voltage source converters using IGBT valves, they do not suffer from commutation failure. So therefore, if there is a fault on the AC side bus, and there is AC side voltage collapse, the commutation failure will not take place there because there is nothing like commutation failure. So therefore DC bus voltage will remain constant. I mean it can maintain the DC bus voltage constant. DC bus voltage will be recovered very fast. And since this, just now when we were discussing the operating principle of HVDC Light, this converter can supply the reactive power. It can absorb as well as supply the reactive power. And if the voltage on AC side decreases because of fault, so it can provide the reactive power support quickly. And by providing the reactive power support, it can provide the voltage support. So it can raise the voltage of this bus before even fault is recovered. And therefore the AC side voltage will recover very quickly within fraction of a second or within a few milliseconds. And then fault may take a few seconds to recover, but your converter will not, HVDC Light will not wait for the clearance of fault. Since there is no commutation failure, so DC side voltage will not become equal to 0, and simultaneously it will supply reactive power to the point of fault and provide voltage support of this bus, and AC side voltage will recover very quickly. So this is the advantage of using HVDC Light in hybrid AC-DC transmission systems. Why it is called hybrid AC-DC transmission system? Because it comprises of pure AC transmission system and DC transmission system. So this is hybrid. Now you can have hybrid AC-DC power transmission system by having AC transmission and classical HVDC. But in modern trend is that classical HVDC system is not used. This HVDC Light is used. It results in better stability of entire this transmission system. It damps oscillations very quickly, and in the event of fault on this side, unlike a classical HVDC system where the voltage recovery or DC voltage, AC voltage recovery takes time, using the HVDC Light, the recovery of AC voltage is very, very quick. It takes place within milliseconds or within fraction of a second. So this is the first application of HVDC Light or VSC HVDC, that is in AC-DC hybrid transmission systems. The second application I will discuss very quickly, HVDC Light in multi-in-feed HVDC systems. HVDC system. What is multi-in-feed HVDC system? Let me first of all draw the diagram and then I will explain. So this is your multi-in-feed HVDC system. This is converter transformer. This is your classical HVDC system using current source converters. Converter transformer on the other side also. Then this is your modern HVDC system, VSC HVDC or HVDC Light, using voltage source converters. Similarly on this side also you have voltage source converters. Okay, fine. And then you have again classical HVDC system using current source converter. This is current source converter. This is another current source converter. Okay, now this HVDC transmission system comprises of two classical HVDC links. This is classical HVDC link. Let us call this link as link 1, HVDC 1, and this link is HVDC 2, classical HVDC. And what is this? This is HVDC Light. Okay, let us see how HVDC Light helps here. Let us assume or suppose a single phase to ground fault occurs. Phase to ground fault is set at AC bus of HVDC 1 inverter. This is HVDC 1 inverter. So this is its AC bus. Suppose a line to ground or phase to ground fault F occurs here. So what will happen? Let us suppose the inception of fault is the beginning of fault. The fault begins at 4 seconds. 4 seconds and duration. Say after t equal to 4 seconds, fault occurs and duration of fault is 0.1 second. 0.1 second means 5 cycles, because one cycle is 20 milliseconds and 5 cycles is 100 milliseconds. 100 milliseconds means 0.1 second. The fault is there for 0.1 second. After t equal to 4 seconds, phase to ground fault occurs on the AC bus here, and the duration of the fault is 0.1 second. So what will this do? HVDC Light 1, HVDC 1 and HVDC 2 both will suffer commutation failure. Commutation, this AC bus voltage fault will result in commutation failure of both HVDC 1 and HVDC 2. Both will suffer HVDC 2 inverters. Both inverters, this inverter as well as this inverter, will suffer commutation failure. And because of the commutation failure, the DC side voltage here will fall. DC side voltage will fall. And there will be time, the recovery time for recovery of AC voltage will take, it will take time. Okay. Let us suppose, now how will HVDC Light help here? With HVDC Light, now since you have HVDC Light, what will this HVDC Light do? It will provide reactive power support to the AC bus. Suppose this is the AC bus, here fault had occurred. Okay, यहाँ पे fault occur हुआ था. So reactive power will be supplied and voltage support is provided. So therefore, since this as soon as this AC side fault occurs, this inverter and this inverter both suffer commutation failure, and DC bus voltage of HVDC 1 and HVDC 2, the DC bus voltages DC line voltages will also collapse, they will fall. But simultaneously what will happen? The controller of this HVDC Light will act very quickly. It will supply the reactive power Q. It will inject the reactive power supply and inject that reactive power into the AC bus, and it will provide the voltage support of this AC bus, and therefore it will raise the voltage of AC bus. If earlier AC bus voltage was fallen, it had fallen to 0.2 per unit. Now it will fall only to 0.8 per unit. So it will not allow it to go down from 1 per unit to 0.2 per unit. It will decrease it to only 8 per unit. That means only 20% fall. Okay, so therefore AC bus voltage support will be provided, and because of that, the recovery of AC voltages and clearance of commutation failures of both the converters, these inverters will take, it will take place, and recovery of these AC voltages will be very fast. So because of this, AC bus voltage is not let go down deep. Okay, and this results in quick recovery of DC side and AC side voltages of HVDC 1 and HVDC 2. Therefore, HVDC Light, which is in the middle of two classical HVDCs, it will improve the stability of overall in-feed system. Any fault on the AC bus, if this HVDC Light would not have been there, then the fault of AC bus would have resulted in the commutation failure of this inverter as well as this inverter, and recovery of AC voltage and DC line voltages would have taken a lot of time. Okay, but in presence of this HVDC light, as soon as this AC bus fault occurs, it results in commutation failure of these two converters, and DC bus voltages also fall, DC line voltages also fall, but it immediately provides the reactive power Q support to this bus. It raises the voltage of bus. It does not let it go. It does not let the voltage of this AC bus go down. Okay, so AC bus voltage may go down by just 10 to 20%. So therefore, the commutation failure will be over here, it will be over here, therefore there will be quick recovery of DC line voltages and also AC side voltages of both HVDC 1 and HVDC 2. This is how HVDC Light helps in multi-in-feed system. Therefore, we can say that HVDC Light technology or HVDC Plus technology or VSC HVDC technology is very useful in improving the overall stability of AC-DC hybrid transmission systems, and also in multi-feed HVDC systems. It improves the stability and it results in quick recovery of DC side voltage and AC side voltage in case of fault. So this is all about HVDC Light. Therefore, the main application of HVDC Light is transmission of small amounts of power over small distances economically. And there is independent control of active as well as reactive power. This is one of the excellent features of HVDC Light. HVDC Light can operate in all the 4 quadrants. It gives 4-quadrant operation. And therefore, with the help of these two applications, you have seen how HVDC Light or HVDC Plus results in better stability of hybrid transmission systems and quick recovery of voltages, AC bus voltages and DC side voltages in the event of fault. So that is all about HVDC Light and HVDC Plus. And modern trend is that this HVDC Light is used very frequently for wind farms, land wind farms and offshore wind farms, because there the power generation is not high. Power is generated, say 100 megawatts or 200 megawatts or 150 megawatts. Small powers are generated, and this power is to be transmitted over short distances. Then through underground cables, this power is transmitted using HVDC Light technology, and it is fed to the load centers. So with this, I end my today's lecture on HVDC Light or HVDC Plus. We are left with the last lecture, that is multi-terminal HVDC systems and some of the practical applications of HVDC systems in wind farms and offshore these wind farms. So inshallah, in our next lecture, we will take up multi-terminal HVDC systems, and that will complete our module 5, and in fact that will be end of the syllabus. I advise all of you to go through today's lecture, and in the event of any problem, please get connected to me. Thank you.